All right, doing 6.6 now. So 6.6 is just another application of these integrals. This is all about finding center of mass. So in physics, and I think most of you are probably taking physics or have taken physics along with this Calc 2 class. You probably at least mentioned center of mass in those classes, but we're just going to do a little bit more in-depth mathematically how the center of mass works. And we're going to do it in a two-dimensional space instead of just a one-dimensional space. But at least to start it off, we're going to look at a one-dimensional space here. So let's say that we had some fulcrum, and then on that fulcrum we have a weightless line, and then on these lines, on this line we have some masses. So maybe three of them. This is what the book uses, so I'll just kind of go along with the book here. We have these three masses, all with a different mass, M1, M2, and M3, and they're all at different locations. So this is going to be X1, this one X2, and this is X3. We're just going to assume that the fulcrum here is at the origin on this number line. It doesn't have to be, of course, but if it is on the origin, then X1 would be a negative number, X2 and X3 positive numbers. Now what we would need from this, if we're talking about center of mass of the system, is we're going to talk about something called torque. Torque you want to think of as a force on whether this system is going to rotate counterclockwise or clockwise, depending on how the weights are distributed in the system. And to find the torque of the system, all we do is we add up all of the different moments with this gravity constant to them. So we're going to take the gravity constant times m1 x1. So that's the moment. Well, the moment is just the m and the x. The g is just kind of to make it into a force instead. Plus, same thing for the second mass, the gravity constant m2 x2 plus, and then the gravity constant m3 x3. Okay, so this is the torque. This is more the physics side of things. To get to the math side of things, what we're going to do is we're going to take out these gravity constants. So instead of talking about a force with torque, we're going to be talking about something that's kind of, it's not really a physics application necessarily, it's the moment. And we're going to be looking at the moment about the fulcrum, and we're just going to assume that the fulcrum is at the origin. So this moment about the origin, all we do is we take the same thing from up above, but we're going to just ignore the gravity constant. So you're just taking all the individual moments of each of these masses, and then adding them all together. Okay, so cool. From this, we can actually find the center of mass, because if we have the moment, if this comes out to be a positive number, that means it's going to be rotating clockwise. If it's a negative number, it's going to be rotating counterclockwise. But if we can find the location where the moment or the torque in general comes out to be zero, then we can get the center of mass. The center of mass we always label with a bar over the top of it. And in this instance, it would be this moment that we would have all divided by the total mass. And that's going to be a pretty common way of finding the center of mass of a system here. So this is just a one-dimensional case. We're going to jump into a two-dimensional case now. So the book does a little bit more transition from 1D to 2D, but I'm just going to jump right into it. So if we had some kind of area, let's say this is a flat area of glass or stone or whatever the material is, it does not have to be a constant density. What I mean by that is maybe here on the right-hand side, it's a little bit denser and heavier than here on the left-hand side. But we are going to need it to be a symmetrical density, or I guess more, it has to be a density that is constant along either the x-axis or the y-axis. So maybe it's some kind of glass that gets thicker and thicker and thicker as we move along the x-axis, but does not get thicker as we move along the y-axis. Okay, anyway, what we're going to do now is we're going to try to find the moment of this plate. And to find the moment of this plate, we're going to have to do slices again. Okay, so depending on what is easier to do for our problem, we're going to either do vertical slices or we're going to do horizontal slices. So let's say we do have a vertical slice of this system here. Over here, let's look at another system where maybe we're doing horizontal slices instead. Again, these just depend on what's easier to define based on the problem that we have, and we'll look at different examples. With these slices, and we are going to have an infinite number of these slices, we don't just need the slice itself defined, we need to find the center of mass of each of these slices. And because we're going to assume that the density is constant on the slice, that means that the center of mass of the slice is going to be right in the middle. Same thing with horizontal slices as well. The halfway point is what we're going to call the center of mass of that slice. And the center of mass of the slice, we give a name. There's a probably more official name to it, but I call it the wiggles. So this is going to be X wiggle, Y wiggle. This is the center of mass of each of the slices for our system. Then, if we treat each of these center of masses as their own individual mass and looking at it as a one-dimensional case, we can find the moment in that direction. Okay, so there's going to be quite a few formulas coming forward here. They're going to look very daunting, but I promise you that they're not too bad. So we're going to have to find the total mass M. We're going to get the total mass by integrating over something that we're going to call dm. dm is the differential of the mass. So you can think of dm as being the mass of each slice. And I'll show you how to come up with this here as we do a problem together. The moment about the x-axis and then the moment about the y-axis. The moment about the x-axis is how likely the system is to rotate around the x-axis. Again, if it's positive, it'll rotate around it clockwise, negative counterclockwise. Same thing with the moment sub y. The moment about the y-axis is going to be how likely the system is to rotate around the y-axis counterclockwise or clockwise. So we are going to have to do the one-dimensional case twice to get the moment of x and the moment of y here. To find the moment of x, it's going to be the integral of y wiggle dm. The moment about the y-axis is going to be the integral of x wiggle dm. So unfortunately, you are going to have to do 3 separate integrals to answer these center of mass cases for the most part. But once you have those 3 integrals done, then you can find the center of mass. So the center of mass of my system is going to be a point now, x bar, y bar, where we get x bar by taking the moment about the y-axis and dividing that by the total mass. And we find y bar by taking the moment about the x-axis and dividing by the total mass. There is a page in the book that has all of these formulas nice and concise. So just to bring the book up here, this is on page 356. I don't know why I tried to use my pen. Just use the mouse. So here we go. So this is all the equations. This is also on the formula sheet if you just want to use the formula sheet for the test. Instead of having to go back and forth to the book here. But the moment about the x-axis, integral over y wiggle dm. Moment about the y-axis, integral over x wiggle dm. The total mass, just the integral dm. Then once you do these 3 integrals, the center of mass are going to be these ratios here. All right, so in the next video, we're going to go through an example in both different cases, and then maybe a more complicated example after that.